All right, so ready to dive into some really cool machine learning research?
Absolutely. Always up for that.
Awesome.
Yeah.
So today we're looking at this paper. It's called Denoising Hamiltonian Network for Physical Reasoning, which, yeah, it sounds a bit intimidating at first glance, but trust me, the ideas behind it are super interesting.
Oh, yeah, definitely. And the implications, I think, are pretty huge for the future of how we think about physics and machine learning coming together.
Exactly. So just to give everyone a quick overview, this paper basically introduces a new kind of machine learning framework.
Yeah.
They call it DHN, short for Denoising Hamiltonian Network. And it's kind of like a way to combine the elegance of Hamiltonian mechanics, which is all about understanding physics through the lens of energy, with the flexibility and power of neural networks, which are, well, they're kind of the workhorse of modern machine learning.
Yeah, and that's really at the heart of what's so exciting about this work. In the field of ML, we're always searching for ways to make our models smarter, more capable. And one really promising avenue is to actually start incorporating fundamental physics into the learning process.
Right, because traditional physics-based models can be really accurate, but they often struggle when you throw them into the messy, complex, real world. This DHN framework, I think, is trying to solve that problem.
It is, and the authors outline these three key innovations that make DHN stand out. First, DHN can capture long-range patterns in how physical systems evolve over time. It sees the big picture, not just one step at a time. Second, it has this built-in mechanism to kind of clean up noisy data, which makes the predictions way more accurate. And third, it's designed to be able to handle a bunch of different physical systems all within the same model.
Okay, so this is definitely sounding like a step forward in machine learning, but what kinds of problems did they actually test it on?
So they really put it through its paces with a whole range of tasks. We're talking predicting the trajectory of objects, like where they're going to move, and then also being able to fill in missing parts of those trajectories, like if you only have partial observations. And get this, they even tried using DHN to infer the underlying physical properties of a system, things like mass or friction, just from limited data.
Whoa, hold on. So you give it some data about how a system is behaving, and it can tell you what the system is actually made of.
Exactly. It's like giving the model a few pieces of a puzzle, and it figures out what the whole picture looks like, a fundamental rules governing that puzzle. They also did this really cool thing where they took sparse, low-resolution trajectories, think of it like a blurry, choppy video, and DHN was able to generate a full, detailed, high-resolution version, like upscaling reality based on physics.
That's amazing. It's like you can see through the noise and figure out the true underlying motion. So today we're going to break down this DHN framework and really try to understand why it's causing such a stir in the ML community. And more importantly, what it might mean for the future of AI and, our understanding of the physical world. Okay, where do you think we should start?
Well, I think it helps to first understand the context. For a while now, researchers in this area of physics-informed machine learning have been trying to figure out the best ways to kind of bake our knowledge of physics into AI models. And a lot of the existing methods out there, they tend to focus on what you might call local predictions. Like they look at the current state of a system and just try to predict the very next state, baby steps.
Right, and that makes sense. It seems like a natural starting point.
It is. But the problem is, real-world physical systems, they're not always so simple. Their behavior unfolds over time, and those individual steps, they're all connected. And so this paper is arguing that to really understand and reason about those systems, we need to look beyond just those immediate updates.
So we need models that can understand the connections between those steps.
Precisely. That's where this idea of DHN, with its ability to capture long-range dependencies, comes in. And the authors point out that this shift, from local to more global reasoning is a big deal.
Makes sense. So what were some of the earlier attempts to incorporate physics into machine learning?
So there's been a lot of work on incorporating physics into neural networks. The goal is to give the network a sort of innate understanding of the rules of the game. And one of the most notable approaches is Hamiltonian neural networks, or HNNs. They're really good at predicting how a system will evolve over time while still respecting these fundamental principles, like the conservation of energy.
Oh, that's cool. They sound like they're pretty good at simulating how things move.
They are. But traditional HNNs, they typically focus on a single system at a time, and they often assume that the data we have is sampled at regular intervals. You take a measurement every second. But in the real world, data can be messy, and things don't always happen at such nice, even intervals.
Right. right? Like imagine trying to track the movement of a bird in flight. It's not going to conveniently hit a specific point every second.
Exactly. And then you have these other really powerful techniques like physics-informed neural networks or PNNs and Fourier neural operators or FNOs.
No, I've heard of those. They're like the rock stars of scientific machine learning, right?
They kind of are, and for good reason. They've had a ton of success in solving problems that are described by partial differential equations, or PDEs. Like, think about modeling how fluids flow or how heat spreads.
Oh, I see. So they're really good at those kinds of continuous processes.
They are. But when it comes to more discrete systems, like the kind that this paper is focused on, where things move in sort of distinct steps, they're not always the best fit, especially when the data isn't sampled perfectly evenly in time. So that's where DHN tries to bridge the gap between these different approaches.
So it's trying to take the best of both worlds, the accuracy of physics-based models and the flexibility of neural networks. It's like trying to find a common language between these different ways of understanding the world.
Exactly. And it's similar to what's happening in other areas of machine learning, too. The paper uses the example of predicting stock prices. So traditional time series models might just focus on recent price movements, those local updates. But what if you had a model that could also understand broader economic indicators and long-term market trends, those non-local relationships?
That's a good point. It'd probably be way better at predicting the market.
It would. And it might even be able to figure out the underlying economic factors just from looking at the stock prices.
So DHN is trying to do something similar, but for physical systems.
Exactly. It's trying to understand those bigger, more fundamental forces that are driving the system's behavior. So instead of just learning a direct mapping from one state to the next, DHN defines these things called state blocks. And they're basically chunks of the system's behavior over a certain period of time.
Okay, so instead of looking at each individual frame of a movie, it's looking at whole scenes.
Exactly. And then what the network learns are the relationships between these blocks. So it's not about predicting just the next frame. It's about understanding how the story unfolds over those scenes.
Wow, so it's learning about the whole narrative of the system. That's a really cool way to think about it. So what you're saying is the motivation behind this paper was to create a model that could really leverage those global physical principles, like energy conservation, within a neural network framework.
That's exactly it. Because we do have elegant ways to describe physical systems mathematically. Like we have these things called analytical solutions, but those often only work for really simple systems. And then you have numerical methods based on those PDEs we talked about, but they can be very computationally expensive and, they're still inherently local.
I see. And those limitations, they're what the researchers are trying to overcome with DHN.
Exactly. It's about bringing that broader, more holistic understanding to these complex real-world systems where the traditional approaches kind of struggle.
Okay. This is all making a lot more sense now. So how about we dive into some of the historical context that led up to this work? What were some of the key milestones that paved the way for DHN?
Well, using computation to try and understand physical systems, that's actually been going on for a long time. It even predates modern machine learning as we know it. I mean, think about those early AI approaches, like rule-based expert systems. They were trying to encode physics directly into those rules. But those systems, they were super rigid.
Yeah, I remember learning about those. Like if the rules weren't absolutely perfect or if the real world, did something unexpected, the whole thing would just fall apart.
Exactly. And that's because they couldn't really learn or adapt. They just followed the script no matter what. And then neural networks came along and they brought this whole new paradigm, learning directly from data. But those early neural networks, they were kind of like the Wild West. They could learn to mimic the behavior in the data, but they often had a really hard time generalizing to new situations or even respecting those basic laws of physics.
Right. They didn't really understand the why behind what they were seeing.
Exactly. And that's where the field of physics-informed machine learning really started to emerge. And, one of the most important developments in this area was the creation of Hamiltonian neural networks, those HNNs we talked about earlier.
So HNNs were kind of a bridge between those rule-based systems and the more free-form neural networks.
That's a great way to put it. They brought some structure and physical grounding to the learning process. But as we discussed, they still had some limitations. Those issues with long-term dependencies, non-uniform data, and modeling multiple systems. And that's where DHN comes in.
So DHN builds on those earlier successes, but also incorporates ideas from other areas of deep learning that have really taken off in recent years.
Right. Like, think about techniques like masked autoencoders and diffusion models. They've been incredibly powerful for learning really complex representations, especially in things like image generation and natural language processing. And what the researchers behind DHN did is they took inspiration from those techniques, particularly the concepts of masking and denoising, and they integrated them with the Hamiltonian formalism.
So they borrowed from these cutting-edge areas of AI and applied those tools to the problem of physical reasoning. It's kind of like taking a technique that works really well for understanding images or text and using it to understand the physical world. So is that the core innovation of DHN, like the main thing that makes it so special?
Well, it's definitely one of the key innovations, but there's more to it than that. There's this growing need for ML models that can not only predict what's going to happen, but also truly grasp the why behind it. Especially in fields like scientific discovery and engineering, we need models that can provide insights into the underlying mechanisms that govern physical systems.
Right.
And that's where DHN's ability to capture those long-range dependencies and to handle those messy real-world scenarios becomes so important.
Right, because if you can understand the why, you can start to design and control systems in ways that we never could before. It's about going beyond just prediction and moving toward true understanding.
Exactly. So to kind of recap the big picture, DHN really does bring a lot to the table. First, it extends what Hamiltonian neural networks can do, taking them beyond just predicting the very next state. The blockwise approach allows it to understand those long-term connections, those dependencies that stretch across time. And then the denoising mechanism that makes it super robust to noise, which is a huge deal in the real world where data is almost never perfect. And it also lets it do things like fill in missing data and even increase the resolution of sparse observations. And then, the global conditioning aspect, that opens up some really exciting possibilities.
Like what?
Well, building models that can understand and predict the behavior of multiple completely different physical systems all at once. It's like having a single framework that can reason about, say, the motion of a pendulum, the flow of traffic, and the spread of a disease.
That would be incredible. A universal theory of AI physics. So does DHN actually work? Did they show that it lives up to all this hype?
They did. In the paper, they present a bunch of experiments where they test DHN on these different physical systems and on all those different tasks we talked about. And the results, they're really promising. DHN consistently performs as well as, or even better than, the existing state-of-the-art methods. And it shows this really impressive ability to generalize to new scenarios, which is super important if we want to use these models in real-world applications.
It's like DHN has taken a big step toward making physics-informed machine learning more practical and more powerful.
Exactly. And that's why I think this paper is so exciting. It's not just an incremental improvement. It's a real conceptual leap forward. And it's definitely going to shape the direction of research in this field for years to come.
Absolutely. So now for our novel notion segment, where we take some of the ideas from the paper and, try to spin them forward, see where they might lead. And I got a question for you. Building on this idea of DHN learning the underlying physics, what if we tried to integrate DHN with something called a differentiable physics engine?
Differentiable physics engines. That's interesting. So you're talking about those computational tools that simulate physical systems, but in a way that allows you to calculate gradients, right?
Right. You can tweak the parameters of the simulation and see how those tweaks affect the outcome. So I'm picturing this scenario where DHN learns those high-level dynamics, the overall patterns of how a system behaves, and then you use the differentiable physics engine to handle the really detailed, fine-grained simulation.
I see. So DHN provides the strategy, and the differentiable physics engine handles the tactics. DHN figures out the general rules of the game, and then the engine lets you play out those rules in a super precise way.
Exactly. And this could be a game changer for things like robotics. Imagine you want to teach a robot how to do some really complicated task, like manipulating objects in a cluttered environment. DHN could learn the overall strategy for, say, grasping an object, and then the differentiable physics engine could allow for superfine control of the robot's movements based on that learned strategy.
That's a really cool idea. And it's kind of in line with what's already happening in robotics research. People are starting to combine learning with those classical simulation techniques more and more. And you know what? What if we could take this even further? What if we could use DHN to actually learn the parameters of the underlying physics engine itself?
Whoa, hold on. So, the AI is not only predicting how a robot is going to move, but it's also refining its own understanding of the robot's physical properties, like its mass or the friction in its joints, just from watching it move.
That's the idea. It would be like the robot is constantly calibrating itself, making its internal model of the world more and more accurate. And that could lead to some incredible advances in robotics, especially for things like manipulation and locomotion in complex environments.
Absolutely. It would be a huge step towards robots that can truly learn and adapt in the real world. Okay, so now let's go full sci-fi here. What if we could use something like DHN to actually discover new physical laws, or those conserved quantities that physicists are always looking for? You know, those fundamental rules that govern how the universe works.
Whoa, that's a big one. So you're thinking, like, we train DHN on a huge data set of all kinds of different physical phenomena, maybe even data from experiments where we don't fully understand the underlying physics, and then see what it comes up with.
Exactly. Like maybe the patterns that the network learns, or even the structure of the network itself after training, could reveal some hidden relationship or symmetry that physicists haven't noticed before. It'd be like having an AI physicist that can analyze data in ways that we just can't wrap our heads around.
I mean, it's definitely speculative, but it's not totally crazy. Right? Think about training it on tons of data from like fluid dynamics simulations or astronomical observations. Who knows? Maybe it could uncover some new principle or conserved quantity that's completely hidden from us in the equations.
Right. I know it's a long shot, but the possibility of AI aiding in fundamental scientific discovery like that is just so mind-blowing.
I know. And, even if it doesn't lead to like completely new physics, the ability of these models to analyze huge data sets and find those hidden relationships, that's going to be incredibly valuable for scientific research across all kinds of domains.
Well, that brings us to the end of our deep dive into the Denoising Hamiltonian Network, and wow, there's so much to unpack here. But I think it's safe to say that this research represents a big step forward in this whole quest to integrate the power of machine learning with, the fundamental principles of physics. It's like a new era of understanding the world through AI is just beginning.
And I think the key takeaway is that DHN isn't just about making better predictions. It's about building models that truly understand the underlying mechanisms, the why behind the what. And that's going to be crucial for all sorts of applications, from robotics and engineering to scientific discovery and beyond.
Exactly. So if you're interested in learning more, definitely check out the original paper. We'll have a link in the show notes. And that leaves us with one final question to ponder. How do you think frameworks like DHN will ultimately shape the future of AI and our relationship with the physical world?
Another great question to ponder. Thank you for joining us on this deep dive.
Until next time.